Oh, there it is. I get more of it than that. How about that?
There's always a simple solution.
Okay. Can I ask everybody this before? We have the exam on Wednesday the 8th of May at class time. Would that present a problem to anyone? No. Good.
You did ask.
I did ask that? Okay. Okay. Yeah, if there's any problem, then we'll have to go to the dean's list and use that. But barring any conflicts, we're going to come in at the same time on that Wednesday. Of course, there won't be anything on Monday because that's exam week. So we'll just meet on Wednesday, do our thing, which will be chapter 9.
So this, you're talking about 1 week now, right?
Maybe 1 week or 2 weeks. Yeah, 1 week.
2 weeks.
2 weeks. Yeah. 2 weeks from today. Okay, let me identify this for the camera.
Yeah, that should be fun. As long as I don't get mandated at work. As long as my car stays together in one piece.
Who's that?
But at our age, I'm working in a hospital, I'm not scared. That we paid enough to be able to make it. Like working in Johnson, that can't do it.
Cool, man.
Yeah, but then once the penalty. Okay.
Okay. Shows up. All right. Let's look at some more bonding. Last chapter we started off with ionic bonding and ended up with a model called the localized electron model. And we used a subset of that called VSEPR, or valence shell electron pair repulsion, to determine what the shape of the molecule might be. In this chapter, we're going to extend that because there are some things that the localized electron model in its current form that you understand doesn't solve. So we're going to have one more tweak to that model. Then we'll move into something that explains everything pretty well. So let's start with methane. Methane's a problem. And here's why. Methane is composed of carbon and hydrogen, and they both come from the nonmetal side of the periodic table, which means that their bonding is covalent. They share electrons. Okay. The localized electron model says that since electrons are assigned to an atom and the bonding occurs due to overlap of orbitals of those particular electrons. In hydrogen case, it's just the 1s. Each one of these has a 1s. If we write the electronic configuration of hydrogen, it's just 1s. So the s orbital contains, that's not a problem. The problem is with carbon. If we do the electronic structure for carbon, we have 1s2, 2s2, 2p2. Okay? Now, if we're going to overlap orbitals, we've got 2s orbitals, which are spherical, and then we've got 2p orbitals, which are kind of like the dumbbells. Okay? So logic would have it that two of these hydrogens are going to be in one sort of configuration, and the other two are going to be in another configuration, because one will overlap this p orbital and the other overlap that. Right? So we should see an irregular structure for methane, but we don't. We see a tetrahedral structure, which is what the VSEPR would predict. Right? The EPR says 1, 2, 3, 4. 4 electron groups. And the regular structure for that is tetrahedral. Okay, and that's what we see. But that doesn't explain why, right? That's just says this is how you do it. When we try to explain why, we can't, because we have 2 electrons in s orbital and we have 2 electrons in p orbitals, and those overlaps will not give us a regular structure. So that's the problem. And of course, tetrahedrals always have 109.5 degrees bond angle. So, with this type of structure for carbon, we're going to have to do one of 3 things. Right? Remember what I said about theories and their models. You have 3 choices. When the model doesn't satisfy, doesn't provide the proper prediction, you can either tweak it, change it just a little bit, or you can restrict its use. Say beyond these boundaries, it's no good. Or you can throw it out and start over again. At this point, we're going to tweak it and restrict its use. Okay, so what's the tweak? The tweak is called hybridization. We're going to take these 2 orbitals and combine them. Now we need 4 of them, and hybridization says that when we do something, when we combine these, it's like we put them in a blender and then pull them out. When we combine those, we have to end up with the same number of orbitals after the hybridization that we started with, right? So we've got one s orbital here, right? And we're going to need three p orbitals, right? Because we've got 4 hydrogens, we need 4 orbitals to overlap, right? So even though we only say that there are 2 electrons here, we know that with the p electrons, the p orbitals, you have an x and a y and a z. So we're going to take s and mix with 3 p's. And this is our new hybridized orbital, the sp3. And we have 4 of those. So out of these 3 and that 1, we get 4 of these that are all the same. Okay. So that's our tweak. That's how we explain that the methane molecule is tetrahedral based on the localized electron model. So sp3 hybridization, I'll put it over here on this side because we're going to have some others. So if we take an S and 3 P's, we get that hybridization, and the structure that comes out of that is tetrahedral, because you have 4 orbitals regularly spaced. It has to be a tetrahedron. Okay. Now, what do the energies of these orbitals look like? Well, if they're all the same, they all have to be the same energy, right? But they're a combination of 2 different energy levels, the S and the P. So the combination is somewhere in between. You have these 3 P's combined with that S, and you get these 4 sp3 hybridized orbitals at that energy level. And some chemists or chemists have proposed this structure for this electron distribution for the sp3 hybridized orbital. See, there's your S, there's your 3 P's, and now that we have all of them the same shape, they have to point to the apex, the apices of the tetrahedron. And that's why this one's pointed that way, that one's that way, this one that way. So that gives you the potential for producing a tetrahedral structure out of these disparate orbitals. Okay. Always keep in mind that we don't do this kind of stuff just because we think it's fun. I mean, some chemists probably do in their minds. But their ideas aren't accepted unless we need this type of a tweak. Right? And the reason we need it is because methane is tetrahedral. That's been proven, measured. So we have to explain it, and this is the explanation. So what about this one? C2H4 is called ethylene. So it's going to have 2 hydrogens on each carbon. Right? And in order to, the carbon has 4 valence electrons, so we've only used 3 of them here. So we've got another one. We've got 1 here, and this one's got an extra one. And these 2 are going to combine and produce another bond, so that we get 2, 4, 6, 8, 2, 4, 6, 8. So each carbon has an octet. So that's the Lewis structure for ethylene. Now, similar problem. What does the VSEPR say should be the structure, or the the structure around this carbon? They're both structured the same, so we talk about one, we talked about the other. Right, 1, 2, 3. So 3 electron groups means what? Trigonal planar. Okay? But we got the same problem. We got S's and P's. And you don't get a regular trigonal structure with one S and however many P's you need. So how many do we need? How many regular orbitals do we need to produce this arrangement? 3. 3 regular trigonal pointing orbitals in order to overlap with the hydrogen and the other carbon. So we take one of the S's, now we only need 2 P's. So we just hybridize one S and 2 P's, that gives us 3 regular trigonally spaced orbitals. And that accounts for this structure. So whenever you have an Sp2 hybridization, you get trigonal planar geometry. Okay? So nobody's clamoring to know why. What happened to the other p orbital? It's unused until this. So each one of them has an unused p orbital, right? Because we only use 2 of them. Right? So there's a third one out there. That's where that other valence electron is located. So these p orbitals overlap, and they give you that extra bond. Okay? Oh, these have names. These guys, we're going to get to that, aren't we? I don't want to jump ahead too far. Yeah, we're going to get to that. So let's do this for now. So the shape is trigonal planar for each of the carbon atoms. And the bond angle is going to be 120 degrees, right? 120, 120, 120. 3 times 120 is 360. So you go all the way around 360. So each of the bonds has to be 120 degrees. Now you're probably wondering, what if we just hybridized an S and 1 P? What kind of geometry would that give? Well, they're going to stick this in there first. Well, I'm just going to go ahead and tell you this. If you only hybridize one S and 1 P, how many bonds can you have around that atom? 2. Because you have 4 of these, you have 3 of these, and you only have 2 of those. So this molecule is going to be linear. We'll get to that one in a second. An example of that in a minute. But first of all, when we have, let's go back to this one, where we start off with like that, like that, like that. These bonds are all sigma bonds. And the characteristic of the sigma bond is maximum electron density is on axis between the atoms. So there's a sigma, there's a sigma. Each of these is a sigma. Anytime you have a single bond, it has to be a sigma. You always have to have at least one sigma before you have any other type of bond. They use a capital sigma. I don't like that one. I like this one. This is a small letter sigma in Greek. So these are all sigma bonds. Now, we already know that for this ethylene molecule, we got another one in there. So that bond is a pi bond. Pi bonds are characterized by off-axis electron density. So when you bend those the p orbitals over to overlap, they can't be on axis because there's already a sigma there. So they're off axis, the pi bonds. You can only have one sigma bond because there's only one axis between the atoms. But you can have a maximum of 2 pi bonds. So an example of that is anybody here do any welding? No? That's acetylene. And we have a sigma, and a sigma, and then we have a pi and a pi. So in this case, 2 groups, the SEPR model says 2 groups is linear. And in fact, it is linear through that carbon atom and linear through this carbon atom. So we only need to hybridize an S and a P because that gives us one here and one there. Okay. That means we've got 2 P's, like a PY and a PZ, that are unused. Okay. So they'll be like this, like that, and then into the board, be like this and that. So you've got those unused p orbitals. Right? For one of the pi bonds, we overlap these, and for the other one, we overlap these. So that gives you 2 pi bonds and 1 sigma. So anytime you have single bonds only, it can only be sigma. If you have a double bond or triple bond, you can have pi bonds. Questions so far? Okay. So this is what an Sp2 hybridization for this particular geometry would look like. These are intermediate energies for the Sp2s. And of course, that's an unused P, unhybridized, so it has to be at the same energy as the parent. So there's your Trigonal Planar outfit.
The carbon-carbon double bond in ethylene consists of a sigma and a pi bond. An Sp2 hybrid orbital on one CH2 unit of ethylene overlaps with an Sp2 hybrid orbital on the other CH2 unit to form the carbon-carbon sigma bond. Now we use a side-on view to show how the remaining unhybridized p orbitals on each CH2 unit overlap to form the carbon-carbon pi bond.
Okay. The stronger of the 2 bonds is the sigma bond. Individual bonds, sigma is stronger than the pi because it's on axis. The electron density in that shared region is between the 2. The off-axis sharing produces a weaker bond. Okay. As an individual, energy, no, that's not the way to do it. Let's just say sigma is a stronger bond than the pi bond. But when you can't have a pi bond unless there's a sigma bond there already. So the strength of the sigma bond is the lowest. Sigma bond is that strong. And then a stronger bond, and this is a single bond, I should say that, single bond, then a double bond has a sigma and a pi. So you combine the strengths, this one and this one, so this one's stronger than that one. And then if you have a sigma and 2 pi's, or a triple bond, this one is stronger than that one, okay? Simply by the combination. Now it's not linear additive because this one's not as strong as that one. So this one won't be double what this one is, even though we say it's a double bond. This one is stronger than that one, but not twice as strong. And this one's stronger than that one, but not twice as, 3 times as strong as this one, okay? The other characteristic that, besides the strength of the bonds, is the length of the bonds. So as the bond gets stronger, the distance between the nuclei shortens. So the stronger bond means a shorter bond. So this one's going to be shorter than that. Right? This one has the greatest distance between the two because it's the weaker bond. And as you strengthen it, they get closer. Okay, so they run opposite one another. So let's take carbon dioxide.
1 o'clock.
Okay, 45 minutes. But we do have another class period. Yeah. We got another class period before the review if we need it. But so I'm going to finish on time today because we have a lab. So what's the shape of CO2 around the carbon atom? All right, CO2, we do our Lewis dot structure. So carbon has 4 electrons. Each oxygen has 6, so that's 12. That's 16 electrons. Carbon's in the middle. Okay, so 2, 4. We have 12 electrons that have to be dealt with. Did I do that right? Yes. Okay. So 12 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we got them all up there. Now we need to make an octet. So the best way to make an octet in this arrangement where you have equals on both sides is to take 1 from each. So we'll take 1 here, take 1 pair there, and that gives us as the most probable Lewis dot structure for carbon dioxide. Now you could draw one where you only have, you take 2 pair from this side and make a triple bond on that side. But remember our discussion of the formal charge. If you calculate the formal charge of one with a triple here and a single there, the values are further away from 0 than they are here. So this is the preferred structure for carbon dioxide. Now, BSEPR says 1 group here, 1 group there, that's a linear molecule. Right? Okay, so if that's a linear molecule, what type of hybridization was required? Sp, right? So Sp hybridization gives us the correct hybridized orbital to overlap with this oxygen, since we have 2. One of them is used for this one of them is used for that one, and these produce the sigma bonds. 2 sigma bonds, 1 on either side. Then we have 2, let's call it Y and Z, 2 unused, unhybridized P's. Here. Like that, like that, like that, like that. Say this one is used to overlap over here. This one is used to overlap over there, so that gives us a pi here and a pi here. Okay? So we still have a linear arrangement. And we have a double bond here and a double bond there. Now, is this molecule polar or nonpolar? What's the electronegativity difference? Which way do the electrons want to go? Toward oxygen. Right? It's got a stronger pull on electrons than carbon does. But they're opposite one another. So they cancel out. That means the molecule is nonpolar. And the bond angle has to be 180 degrees. Right? Bond angle around this carbon, if that's your center, like that, 180 degrees. Okay, we talked about Sp hybridization already. And that's what the energy distribution looks like. We have 2 Sp orbitals because we have an S combined with a P. And you got to have the same number of hybridized orbitals as the atomic orbitals you start with. So we started with two, one s, one p. We need two sp orbitals after hybridization. And that's what it looks like. This is another idea. This came straight out of the book. So we get the overlap here on this side and the overlap here on this side to give us our pi orbitals. Okay. We're not done hybridizing yet. What if we have PCl5? Right. Phosphorus is going to be 5. Chlorine is going to be 7 each, so that's 35. Right. So that's 40 electrons. So we have a P here, 1, 2, 3, 4, 5. Two, 4, 6, 8. 2, 4, 6, 8, 10. So we have 30 electrons left over. If we put 6 around 5 of these, that'll be 30. Right? And that's the octet, 2, 4, 6, 8. So 6 more around each chlorine uses up all the 30s. Okay. Now, here's the problem. If you hybridize all the S's and all the P's, what do you have? You've only got 4 orbitals, right? 4 equally spaced orbitals. Oh, and by the way, what's the shape of this? 5 means trigonal bipyramidal. Right? So if you're going to have 5 regularly spaced orbitals for these bonds to attach to, you need to get another orbital from someplace to hybridize into 5 possible orbitals. Right? That's only 4. So we take one from the D's. So we have 5 dsp3 orbitals hybridized for this molecule. dsp3 gives you 5 of them, and this is trigonal bipyramid. Okay? Now, why do we take a D? Why don't we take another P from somewhere else or an S from somewhere else? Well, look at where phosphorus is located. It's in the third series, the third period. And remember, when n equals 1, 2, or 3, you can only have an s orbital there. But with n equals 2, you can have an s and p. N equals 3, you can have an s, p, and d. So logical at that energy level is to go for this D, not for a P from some other energy level. We stay with the D. That's why we hybridize dsp3 to make 5 orbitals. Now we've got one other possibility. What is it? We have 6 electron groups. That's the hybridization for 5 orbitals. Okay. How about Xenon Tetrafluoride? What's the Lewis dot structure for that? This one's 8, and 4 times 7 is 28. That's 36. So xenon in the middle. And we have fluorine here. 2, 4, 6, 8. 28. And then if we put 2, 4, 6 around each one of these, 6 times 4 is 24. So we have 4 electrons left over. What do you do with the 4 electrons left over? Work from the outside in. So they have to go on the xenon. Okay. That means we have 6 groups. 6 electron groups around that xenon, and 6 means what? Octahedral. That's octahedral electronic structure. Right? So what do we hybridize to get 6 regular hybrid orbitals to make an octahedron? Well, we need another D. We need 2 Ds, 1 S, 3 Ps. That's 2, 3, 4, 5, 6. We have 6 of those orbitals. That will give us a regular electronic structure. And 2 of these hybridized orbitals will contain, one will contain a pair, the other will contain another pair. So D2sp3, 6 of those that we get from that is octahedral. Okay? All right. So, what we end up with is an octahedral structure with fluorines here. Even though we're using hybridized orbitals, we still have to accommodate the lone pair electrons. And they're best positioned above and below. Like that. The reason for that is we need to get them far away from each other as possible. If we put them here and here, they're 180 degrees apart. If we put them here and here, they're only 90 degrees apart. And remember, lone pair electrons tend to balloon. So they got plenty of room down here and up here. That's why the molecular structure for Xenon Tetrafluoride, even with this hybridization, is square planar. Okay. We're good on time. We got a few more minutes. Let me check my notes and see where would be a good place to stop. We don't have enough time for me to get through to. Oh yes, we do. 13:45. Yeah, we got time. So what I'll do is get through to where molecular orbital model starts. We'll stop right there and pick up the molecular orbital. Nothing. We make stuff nothing. So we're going to go through here. And right there, we're going to stop on this side is today. We'll pick it up on 29th with molecular orbitals. Okay, so let's take hydrogen cyanide as an example. We got 1 electron here. We're going to draw the Lewis dot structure first. 4 for carbon and 5 for nitrogen. Right? So that means 10 electrons. Okay. So we got carbon, nitrogen, hydrogen. Hydrogen is full. Can't put any more around hydrogen. So we got 2, 4, 6 electrons left over. So we start from the outside, work in 2, 4, 6. Okay. Now all of our electrons are used up. But we try to make an octet. Okay. We want to make an octet for carbon. Nitrogen's already got one, but carbon wants one. So we're going to take these 2 and those 2 and move them over here. And that gives us 2, 4, 6, 8, 2, 4, 6, 8, and 2 for hydrogen. So that's our Lewis dot structure for hydrogen cyanide. Now, how do we get linear molecule, linear arrangement around that carbon. Because with two groups, it has to be linear, according to the BSEPR. In order to be linear, we need Sp hybridization. That gives us two orbitals, one on this side, one on that side. So these are our two sigma bonds, right here and here. Then we have p orbitals unused. And those p orbitals, actually the hybridization occurs on both sides, but we're focused on carbon right now. But these unused p orbitals overlap, and one of them produces this pi, and the other one produces that pi. Well, I thought it was going to do this. Depending on me to do it on the board. Now, if you were given, we just gave you this one, right? Can you identify which are sigma and which are pi? Of course, that one's got to be sigma. Single bond. This one in the middle is generally taking a sigma. This is the pi. That's the pi. So for this whole molecule, we've got two sigmas and two pi. Okay? All right. Let's take some examples. Okay, they want bond angles and hybridization for the central atom. All right. Let's start with ammonia. We got 5 plus 3 is 8, right? 8 electrons. So we need a nitrogen here, 3 hydrogens. So that's 2, 4, 6. We need 2 more, like that. Okay. The electronic structure is tetrahedral, right? Because we have 4. Now they don't ask for it, but what's the molecular structure for this one? Right? If you draw nitrogen in the middle, and you put these here, and regularly spaced, here, 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 and this hydrogen's in the back. And so you get a triangle on the base, like that. So the molecular structure then is trigonal pyramid. But what is the bond? What is the bond angle? So the bond angle between, say, this one and that one, well, our starting point is 109.5 for a tetrahedron, right? But we know with a lone pair up here, which tends to balloon out, it puts pressure on these bond pairs and squeezes the molecule down. So it's going to be less than that, maybe 108 actual. But what they're looking for here, in case you're wondering on an exam, they're just wanting the starting point, 109.5 for ammonia. Oh, we didn't do the hybridization. So how do you do the hybridization? Well, if it's tetrahedral, it's got to be that one, Sp3. Sp3 hybridization gives you tetrahedral because it's 4 regularly spaced bonds. 3 of them are occupied by bonding pairs, and the 4th one is occupied by a lone pair. Okay? How about, oops, SO2? All right, SO2. So sulfur is 6 electrons. Oh, and oxygen 6, so 3 times 6 is 18. So we have S, 2 O's, that's 2, 4. 14 electrons we have to deal with. 2, 4, 6, 8, 10, 12. That's 12. And the other 2 have to go here. Okay? So now what do we need? Well, oxygen's already got an octet. Sulfur doesn't have an octet. So we got to give sulfur one of these pairs. Right? We could do it from that side, or we could do it from this side. So remember what happens? You have two valid Lewis dot structures. We can have this one or this one. Right? So what do we do with those? Well, one of our tweaks is we resonate. We resonate between the two. But as far as determining the hybridization and bond angles, excuse me, I left out the one here. So now let's see, we have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Okay. So we have 3 groups around the sulfur. So that means we have trigonal planar electronic structure. And molecular structure is what? Just cover up the electrons, right? So with trigonal planar, we cover up those electrons, we get a bent molecule. What's the bond angle? Well, the bond angle on a trigonal planar is 120 degrees. Because you got 3 of them. 3 times 120 is 360. So the bond angle is going to be 120 degrees. What's the hybridization? Trigonal planar is Sp2. So Sp2 gives us this sigma, and this lone pair. And then the unused, unhybridized p orbitals, or 1 p orbital, overlaps and produces this double bond. In this arrangement, the double bond comes on this side. In this arrangement, the double bond comes on that side. The pi bond, excuse me. Pi bond on that side, pi bond on this side. Okay, so it's Sp2 hybridized with 120 degree bond angle. Let's see. Get my bearings. Okay. Just need to finish this slide. We're good. So actually what we're going to have is part 1. We'll do part 2 next week. Okay. Krypton Difluoride. So krypton is where? There's 8 electrons. 2 fluorines is 14, 7 each. So we have 22 electrons that have to be accounted for. Krypton in the middle, fluorine, 2, 4, 18. Okay, so we need 2, 4, 6, 8, 10, 12. 6 electrons left over. Where do they go? They go here, don't they? 2, 4, 6. Now this has 1, 2, 3, 4, 5 electron groups. And 5 means what? Trigonal bipyramidal. That's electronic structure. With a trigonal bipyramidal molecule, it's kind of tricky to tell where those lone pairs go. But the hybridization, of course, is going to be d Sp3 to give us 5 orbitals. The three lone pairs are in three of those orbitals, and these bonding pairs go in the other two. And they're only sigma bonds. There are no pi bonds here, just sigmas. So if we draw the trigonal base structure, and then we have something up here, krypton in the middle. So we have positions for 5 things. If we put the 2 lone pairs up here, and then 1 down here, like this, this, and this, these 2 are fine. They're opposite one another. But this interaction is unbalanced. That's why I think that what we're going to have is the lone pairs are positioned on the triangle, and the fluorines are like that. So the molecule will be linear. Let's see, what would it be if it was the other way? Let me see. Let's do this. That. If we did this, then fluorines would be here and here. It's possible. In which case, the bond angle between this one and this one would be 120 degrees. Where they get 90 degrees? There's only 2 fluorines. Are they saying that one of the fluorines goes up here? There's something wrong with that slide. That doesn't compute. Because if we put the fluorines here, we don't get a 90 degree angle. If we put one of the fluorines on top, like this, yeah, then we get a 90 degree angle. That. But we don't get 120 degrees. So maybe what they're talking about here is not the molecular angles, but the angles between. Now, those are not bond angles. You gotta have a bond to have a bond angle, don't you? So there's something wrong with that slide. I think what happens is the fluorines go here, here, that's 180 degrees, and the lone pairs go there. So I need to investigate this one a little deeper. There's that one right there, the bond angles. We've done CO2 already. CO2 is 180 degrees, it's linear, Sp hybridized. Linear is always Sp hybridized. And then the pi bonds that you get are from the 2 unused or unhybridized p orbitals. How about ICL5? The temptation is to say, oh, there's 5, so it must be trigonal bipyramidal. But what you need to do is say, what's its actual Lewis dot structure? 6 times 7 is 42. Right? Because these are both halogens. I in the middle, fluorine, fluorine. So that's 2, 4, 6, 8 each one. 5 times 8 is 40. So we have 2 electrons left over. They go here. That means actually 6 groups. So this is an octahedral. So what kind of hybridization do you have in an octahedral? D2sp3. And then to determine the bonds, you say, where does that lone pair go in an octahedral molecule? It's more than likely at one of the apexes. Right, so we have I in the middle, fluorine here, 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 and then we have lone pair there and a chlorine here. So the bond angles there, okay, these are definitely 90 degrees. Does it say 180? Okay, so if it's going to claim 180 degrees, one of those chlorines has to be up here. To be 180 degrees. And then there's your lone pair. So if we believe what the authors tell us here, that's the only structure that's valid. But if it were me, I'd put the lone pair up there, which means we only have 90-degree angles. Well, no, okay. I take that back. Look, this is a 90-degree angle. Here, here. That's, but this one across here is 180 degrees. Okay. So that makes sense to me now. If you go from with this as your fulcrum, and then you say your angle is 180 degrees from that chlorine to that chlorine, or this chlorine to that chlorine. But for this one to that one is 90, and this one to that one is 90, 90. So yeah, that's possible. And we can still put the lone pair up there at one of the apex. Okay, this is just a summary. So the BSEPR model is still valid and still useful. It's just in order to explain, to incorporate into the theory why we get those regular structures. Because the BSEPR is more akin, even though it's a model, it's more akin to a law. It just says what happens. Just count up the number of groups and apply a model. But knowing why it happens requires hybridization. That's the whole point of this first part of the chapter 9. Hybridization fixes that problem. Any questions? Okay. So before we break for a lab, what you may want to do is check Blackboard for your individual student grades. You can go in there and check your grade, right? So you can see where I've posted them. If you've got an empty spot or a 0, then you know that you're missing an assignment. Or you sent me the assignment and I hadn't graded it yet. That's why I changed the date also on the course average. So if the date says, say 2 days ago, 22nd, and you turned in something the 23rd, then that definitely means I haven't graded it yet, because when I finish grading them, then I update that date as well as the grade. Okay? And if you're unsure, just ask me and I'll look in my book and see if I'm missing an assignment for you. Okay, so let's see. Officially, we start the lab at 2 o'clock. So let's see, we've got enough for 2 groups. Yeah, 2 groups will be good. Everybody get copies. Let's see if everybody signed in. 6. 4, 6. You got it. Who are we missing? You dropped. Oh, we're missing Nate. Anna had a doctor's appointment. Hannah Trump. We're missing Hannah. Everybody seen Hannah? I didn't know Hannah. I don't know, when I was going to school and college, everybody knew everybody else. But I guess these days everybody comes in from the hinterlands and I don't know you.
Now, on my lab, we were already on this. I've turned in the calorimetry, I also have the molecular weight acid by titration. It's not this.
That's the one we're doing today.
Yeah. Would I be able to get a copy of the molecular? I think that's the one that I messed up one time.
Yeah, I got copies in my office.
Okay. Because I have 2 copies of this. Take one out today, and I think when I went to get that one, I think I might actually.
Oh, you want to get one back? Not that I care, but
So it's my favorite.
I can use it next semester. What you may want to do is when you find your station, go in there and find your station. I've got water started, but it's probably not boiling yet. You want to crank the heat up some so we'll get it boiling. And I assume everybody has reviewed your lab so you know what you're doing. Or is that a bad assumption?